Good students, we are now again in our practical research 2, module 11 in second quarter, which is about analyzing difference of variances. Okay, the learning competencies of this module is, so the learner uses statistical techniques to analyze data, study of differences limited for bivariate analysis. So our topic is about analyzing differences of variance. Okay. So analyzing differences of variance. What is analysis of variance? Analysis of variance, or the ANOVA, is a technique used to test a hypothesis about several means. It is a parametric statistical technique for determining whether the variance in a quantitative variable differs significantly from the expected by chance for a qualitative variable or its interaction with one or more other quantitative variables. So the use of analysis of variance can be either be single factor, one-way ANOVA, or two-way ANOVA. So one-way ANOVA uses one independent quantitative variable with more than two groups. And two-way ANOVA uses two independent quantitative variables. So to illustrate, so we have types of ANOVA. So we have here the null hypothesis for one-way. The severity level of COVID cases does not differ by blood type. So we have blood types A, B, and O, a person. So reasons, a dependent variable here is the COVID level severity, and the independent variable is the blood types. Okay, we have three blood types, A, B, and O. Then two-way ANOVA, there's no interaction effect of the blood type and the age of the patients on the severity of COVID cases in certain city. Okay, here we have our dependent variable, which is the level of severity, and our independent is blood types and age. Okay, so we have here the basic assumptions of ANOVA. So each sample is randomly selected and independent. And number 2, the data in the dependent variable is continuous and normally distributed. Okay, remember these assumptions. 3, the variation between each group being compared is equal for every group, or the variances are equal. So you can test this using the Leibniz test. Okay, to test the equality of variance. Okay, so using the JAS software. So these are the assumptions needed in order for you to use the ANOVA. Okay, so here how to use ANOVA. So this module only focus on one-way ANOVA for beginners in doing research. Analysis of variance ANOVA makes use of F-test to test a significant difference of multiple means, and hence uses the F distribution table, which is on the appendix of this module, or appendices. Okay, we shall demonstrate ANOVA by analyzing the null hypothesis, which follows the. Okay, so there's a step. So step 1, we have the step-by-step computation of sum of squares, mean of squares, degrees of freedom, and the F value. So since the computation of the test statistics is involved, the computations are often organized in ANOVA table. The ANOVA table breaks down the components of variation in the data into variation between treatments or factors and error or residual variation. The ANOVA table is set up as follows. Okay, this is ANOVA table. We have these 5 columns here. First is the source of variation, then sum of squares, degrees of freedom, then mean squares, then the F. Okay, or the result of the ANOVA statistics. Okay, so for the sources of variation, we have the factor treatments, error or residual, then the total. Then sum of squares, this is the formulas to use. Okay, I'll just familiarize these formulas. So this is for the factors, then the errors, then the total. So total, you just add these two values here. Okay, here, the formula here will be illustrated later, how to use it. Then degrees of freedom. So we have k minus 1, so number of k stands for number of groups. Then degrees of freedom for the error. So n minus k, n is the number of elements in our data. Then total, the degrees of freedom, the total is n minus 1. Okay. Then mean squares, so this is the formula. So SSF divided by degrees of freedom here. Then MSE, so for the errors, so SSE divided by degrees of freedom of the error, which is n minus k. Then to get f, you just divide the answer here. Get f. Okay. So here's the legend and each of the formulas there. Okay. So here we have the interpretation table. So decision rule. So computed t value. So if computed f value is greater than the tabular value, so you will reject the null hypothesis. Okay, so take note. So if f is greater than the critical value or the table value, so reject the null hypothesis. Okay, it's clear. Then how to report the findings? To report the findings, consider template below. So test type and use. We have here analysis of variance. ANOVA was used to compare your DB measure among your IB group 1 and IB group 2 and IB group 3. So significant difference between conditions and group. A difference of the DB measure, then IB level. So you have the mean, the SD. And for the IV, so level 2. So M or mean SD, then was it significant or not? And you give the result of the F, degrees of freedom of the error and the factor, then the critical value. Okay, so let's have this illustration. Okay, the study is about how the patient's blood types affect the severity of COVID-19 in a certain city. A medical expert hypothesized that there is no significant difference on the severity level of COVID-19 patients among the types of bloods. So A, B, and O of the patients. So here is our table. Okay, we have patients 1 to 7 and we have different blood types. So A, B, and O. So total we have 21. Okay, our N and our K here is we have 3 groups. So for the 3 blood types. Okay, we have here, so these are the steps to follow. Okay, we have here this table. So I will use this formula now to compute each values, the treatment factor, the errors, total, and so on. Okay. Okay, first, so step 1, we need to calculate the mean of each blood types. So we have here, so the mean for blood type A is 2.43, blood type B 2.29, and blood type O 1.57. So get the overall mean. So step 1, so add all these values. 2.3 plus 2.29 plus 1.57 is equal to 2.10. Then we will now compute the degrees of freedom. So in the formulas, so for factor k minus 1, so we have 3 minus 1 because we have 3 groups or the 3 types of 3 blood types. Okay, so which is 2. The factor for the error, the formula is n minus k. So our n here is 21 because we have 7 patients times 3 types of blood, so 21 all in all patients. Okay, so we have 7 weeks. Okay, 7 weeks. Then we have our respondents here, which is 3 types of blood, so total 21. Okay, so let me clarify that. So then subtract it, the answer would be 18. Then for the total, so n minus 1. So 21 minus 1 equals 20. So that is a total. Okay, or you can simply add these two, 2 plus 18, 20. Okay, then step 2, we'll calculate now the factors, sum of square for the factors. So we have this formula, n times summation of it stands here for the mean minus the, so the mean here is the mean of that group minus the overall mean, then squared. Okay, I repeat. The formula here is n times summation of, or n times the summation of, we have here the mean of our x, example our blood type A, B, or O, and minus the overall mean, which is 2.10. Okay, so we have here. Okay, here, so we have this formula. So 7 here stands for the 7 weeks. So times 2.43, which is the mean of blood type A, minus 2.10, which is the overall mean of the 3 groups, and squared, and plus 7 times 2.29, mean of the blood type A, minus 2.10, the overall mean, squared, plus 7 times 1.27 minus 2.10 squared. So this is the result after simplification. Then our value would be 2.98. Okay, then after that, we have now our SSR for the factors. Now we will now compute for the errors. So what's the formula? Just follow this formula. Just summation of x sub ij minus xj. So it means that this is the ith observation in the group J and the mean of group J. Or simply, so subtract each element in each group by its group mean. Okay, so example, in blood type A, our mean here is 2.43. So we'll subtract each element here by this mean. So 2 minus 2.43 up until you reach this 7th element here, which is 2. This is the computation. Okay, so 2.40 times 2 minus 2.43 squared plus 3 minus k squared. So total will be 5.71. And the same goes with blood type B. So each element will be subtracted to each mean. So 1.29 squared and so on until you reach the last element. So the total would be 7.43. And for blood type O, the same procedure. So the answer is 5.71. And to get the SSE or errors, so you add these 3 values. The answer would be 18.86. Okay. Then we'll now compute for the total. So for the total, simply add the SSR and SSE. So this would be the answer. The answer would be 21.84. Then let's summarize the data in our table. For our factor, so we have here sum of squares, which is 2.98. Okay, and this value is 18.86. So here, then degrees of freedom, so we have 2 for the factor because k minus 1. For the error, 18 because k minus 3, or 21 minus 3, 18. Okay, so get the total. You just add this 2.98 plus 18.86, 21.84, and add this is 20. Then how to get the mean squared? So simply divide SS by the degrees of freedom. Okay, 2.98 divide 2, the answer is 1.49. 18.86 divide 18, the answer would be 1.05. Then to get the ANOVA, so you statistic, you need to get this, divide this 1.49 divide 1.05, the answer would be 1.419. Okay, so I hope you get the sequence in solving for the F statistic. Okay, after that, so we'll now have this analysis. So let's look at the critical value if we are going to reject or accept the null hypothesis. Okay, step 2, interpret the result by comparing the F value to the critical value in the critical appendices. Okay, so 5%. We have here a hypothesis. So there's no significant difference on the severity level of COVID-19 patients among the types of blood. So we have here this table earlier. Okay, you just copy. So our critical value here is 3.55. Okay, so let's analyze if we're going to reject or not. So since our F value is less than our critical value, therefore, so we will accept the null hypothesis. Okay, we failed to reject the null hypothesis. Okay, because it's less than. Okay, interpretation. An analysis of variance was used to determine the significant difference of the severity level of COVID-19 among the blood types of patients. It was found out that the difference in severity level of COVID-19 when grouped by blood types was not significant. So we have F, degrees of freedom 2 and 18. Then the F statistic is 1.419. And the critical value is 3.55. Okay, which is not significant. Okay, so I hope you get the correct answer in computing for this statistic. So you can also solve this using the JAS software. Okay, so make sure you tally the data. So in the module, let's just like this one. So this is our data. So you set up the data in this form. So blood type. So just code it. So blood type O, blood type A and B. Then COVID severity level. Okay. So we have here. Okay. So blood type and COVID severity. So after you set this up, so you can now save it as CSV file. Okay. Look at this file name. So that's CSV. After that, so you open now your JAS. Okay, so this is the JAS now. Okay, so this is our data. We have blood type, then COVID severity. So what are we going to go? We're going to go to ANOVA. So ANOVA. Then so our fixed factors here would be the blood types. Okay, because that is our categorical variable. Our COVID severity, this is our dependent variable because this is continuous variable. Okay, you can have this script statistics and estimates of effect size. Okay, so here's now our result of our ANOVA. Okay, so let's just maximize the screen to okay, so as you can see here, so our F is 1.40 1.409 or 1.4, so decimal difference only in our computation or module. Okay, what is good is still under 1.4. Okay, then our p-value here is 2.70. Okay, so since it is greater than 0.05, so therefore it is not significant. Okay, and for our descriptive, so we have here now our mean and SD. So blood type O, we have 1.571, and blood type A, blood type B, and so on. Okay, so as you can see, so it's very easy to compute it using the JAS software. Okay, then in our effect of estimates, we have this. Okay, so as you can see, it's 0.135. Okay, so it's minimal effect or negligible effect. Okay, so I hope you get the process in solving for ANOVA using JAS and the manual computation. Okay, Okay, let's go to the next example. So let's try this. Okay, let's have here. So let's do this. So there's no significant difference on the academic grades of students when grouped by strand. Okay. So we have here, this is our null hypothesis. So we're going to determine if there is no significant difference of these groupings or the group of senior highs when grouped according to their strand. Okay. So you can set up this type of format in Excel. So you can feed this data in JAS. Okay. So same process as we did earlier. So you get the mean first of the STEM group, the UMS, and ABM. After that, you get the overall mean. Okay. Then after that, you subtract each score from the mean of each group to get the residual errors. Okay, for the factor errors, so you just subtract the mean of each group by the total mean. Okay, multiplied by 5, which is the number of students here. Okay. So okay, so let's answer. So I will just use the JAS software to have a how to check our work. So just do the manual computation while I'll do the automated computation. Okay, so here's the tabulated data in our Excel. So you set up the data in this format. So you put the track or the senior high school track, then the grade. So the groupings here, we have the STEM, UMS, and GAS, then their grades. So we're going to test if there's significant difference among the academic performance. Okay, in each when group according to their track. Okay. So what we're going to do is we need to feed it in our JAS. Okay. So save it as CSV. Okay, I hope you follow. Okay, so this is now our data in JAS. Okay, so after we set it in Excel, so we are going to run it in our JAS. Okay, so you have here our independent variable, which is the track. The independent variable is the grades. Okay, so let's test using ANOVA. ANOVA. So fixed factors would be the track. And the independent variable will be the grade. Okay, you can use the size and the descriptive statistics. Okay, so as you can see here, so this is our data needed in our table. Okay, so you can see the result on the screen. Okay, so our F here is 0.129, our P value is 0.880, effect size is 0.021. Okay, which indicate that there is no significant difference, okay, of the senior high school tracks based on their grades. Okay, so should in your manual computation you should have 1.29. Okay, I hope you get the correct answer on that. Okay, so let's have another exercise in your module. So remember this. So I hope you have it in mind. Okay, let's test ourselves. We have here now. So research title: the effect of method citing. A method of citing the accuracy level of playing darts. So we have here our null hypothesis. There is no significant effect on the accuracy level of the dart player when using right eye, left eye, and both eyes methods of citing. Okay, so we have this data here. So you can set up this again in Excel, then save it as CSV, and you can run it in JAS software. Okay, so same procedure here. You will follow the manual computation. Okay, and you can check it using the JAS software if your answer is correct. Okay, I'll give you time to compute. Okay, so let's check your work. Okay, here is now our data on JAS. So we have this cite method, right eye, left eye, both eye, and accuracy. Okay, let's test using the ANOVA. So our fixed factors would be the cite method, and dependent would be accuracy. And we have this result. Okay, so I hope you can see it on the screen. Okay, I'll just enlarge it a little. Okay, so our result would be 2.355. Okay, so then our p-value is 0.150. So indicating that there's no significant difference, okay, of the accuracy level when using the different types of eye method and using darts. Okay, so I hope you get the answer. So 2.35. Okay, so hope you're able to understand how to compute the analysis of variance manually and using the JAS. So if you have questions and clarifications, so you can PM me in my Facebook account. Okay, so have a nice day.